Hello students, here is a review for exam 3. Now go through these topics very carefully and understand the concepts thereof. Remember that memorization of these problems will not help. But if you really understand how these have been worked out, it will be quite useful for the exam. So the topics for this exam are linear momentum, rotational motion, stress and strain, and finally fluids. So those are the 4 chapters. Let's begin with momentum. Momentum is the product of mass and velocity. It is a vector because velocity is a vector. That means momentum has to have a specified direction. The unit of momentum is kilogram meter per second. So as an example, if you have a 0.1 kilogram object moving at 10 meter per second to the right, it's going to have a momentum of 0.1 multiplied by 10, which is 1 kilogram meter per second. Now, consider that it then hits a wall and bounces back at the same velocity. So what is its momentum now? Its momentum now is not 1 kilogram meter per second, but instead it is negative 1 kilogram meter per second. Why? That's because the velocity is now from right to left. That means the velocity is negative. That's why the momentum is negative 1 kilogram meter per second. So, if you're asked to find the change in momentum, the change is going to be negative 1 minus 1, which will be negative 2. So the change is not 0, it is double. So that's what I'm trying to show here. The change in momentum, change is always final minus the initial. The final is minus 1. Therefore, the change is minus 1 minus 1, which is minus 2 kilogram meter per second, or the magnitude of the change in momentum. It will be the absolute value, and that would be 2 kilogram meter per second to the left. It is to the left. So remember that. Let's take another example where you have an object at a height of 3 meters as shown in the diagram. And from there it's dropped down and it hits the ground and bounces back up, but only up to 2 meters. So it falls from 3 meters and bounces back up to 2 meters. And you're asked to find the change in momentum. Let's assume that the mass of this object is 0.2 kilogram. How would you find the change in momentum in this case? Here you have to consider that initially it has potential energy. Just before hitting the ground, all of that is changed into kinetic energy. So you have to use the idea that mgh, which is potential energy, is equal to 1/2 times mass times velocity square. Using that, you can find the velocity just before it hits the ground. Again, using the same idea and knowing that the height is 2 meters, you can once again use the idea that the potential energy at B is going to be the kinetic energy with which it starts going up. So from there you would get the final velocity. So now you have the initial velocity, which is down, and the final velocity is up. So when you take the change in momentum, just like in the last question, remember that it's going to be negative minus something. So be careful with that. So that is a couple of questions on change in momentum. Now let's move on to conservation of momentum. And conservation of momentum takes place whenever there are collisions. And the idea is that the total momentum before collision should be equal to the total momentum after collision. So mathematically, we can write it as m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. So remember that the prime there is just to denote the final velocities. So these are the initial velocities of the two objects, and these are the final velocities. Now here again, we're going to work out a question, but I'm going to show it to you completely there. But before we go there, remember there are two types of collisions, elastic and inelastic. What is the difference between these two? The difference is that although momentum is conserved in both of these collisions, kinetic energy is only conserved in an elastic collision. Or in other words, kinetic energy is not conserved in an inelastic collision. So that is the difference. So here is a question. So you have an object A, 3 kilogram mass, moving at 20 meters per second to the right. Another object B coming straight at it. That has a mass of 3 kilogram and that is moving at 10 meters per second to the left. After collision, we know that object A, which is this object, is now moving to the right. It continues to move to the right, but now at 5 meters per second. Earlier, it was moving at 20 meters per second, but after the collision, it is moving at 5 meters per second. And the question is, can you find the final velocity of object B? Yes, we can. We apply the conservation of momentum. m1 times v1, which is what I've written here, plus m2 times v2. Remember, v2 is negative 10 because it's moving to the left. Should be equal to m1 times v1 prime plus m2 times what we do not know. That's what we're looking for. So that's a math. Now we can solve it carefully. You get this as 60. Oh, that's not what I intended to. So that is 60. This is minus 20. That's why you have it there. And this is 15, 3 times 5. And then you have 2 times V sub B. Okay, when you do 60 minus 20, you get 40. And then this 15 goes to the other side, becomes negative 15. So that is 40 minus 15, which gives you 25. And then you can solve and find the velocity of B after collision as 12.5 meter per second. Let's also look at the kinetic energies before and after collision. The formula for kinetic energy is 1/2 times mass times square of the velocity. Therefore, the initial kinetic energy is 1/2 times mass of the first object times square of 20 plus 1/2 times mass of the second object plus square of 10. When you do that, you will get 700 joules. Similarly, when you do the final kinetic energy, you're going to get 1/2 times 3 times 5 squared plus 1/2 times 2 times 12.5 squared, which we got. So that gives you 193.75 joules. And therefore, you see what has really happened. The initial kinetic energy, the total, was 700 joules, but the final kinetic energy is only 193.75 joules. That means kinetic energy has not been conserved. Kinetic energy has been lost. So what type of a collision is this? It is an inelastic collision. The loss of kinetic energy is the difference, that is 506.25 joules. So next, let us look at impulse. An impulsive force or an impulse is a large force acting on an object for a very short time. A large force acting on an object for a short time. There are many examples for this. The best example would be hitting the baseball with a baseball bat. Think about the force between the bat and the ball, especially if it's a home run. The force is huge. But what about the time of contact between the ball and the bat? That's very small. Within this short time, the force goes from 0 to a maximum, and then as the ball leaves the bat, it goes back down to 0. So it is not a constant force. That is why we had to define something called an impulse. And what is impulse? Impulse is the product of force and time. The product of force and time. And that is why the unit of impulse is going to be Newton times second or Newton second. And impulse can also be calculated using change in momentum. J is the symbol for impulse, and you can calculate that using either product of force and time or change in momentum. So if you draw a graph between time and force, just take the example of the baseball and the bat. And I told you that the force goes from a 0 to a maximum, back down to a 0 in a very short time. So this is a highly magnified graph. It's exaggerated because this time is really small in real time. And from this graph, we can find the impulse. Do you know how? Just find the area of this graph. So that's the importance of a force-time graph. You can find the area, and that area will give you the product of force and time, which is the impulse. So let's work out a simple question. All right, let me finish shading it. So I think I'm done now. Let's just assume that there is a force which is equal to 100 newtons acting on an object for a small time of 2.0 seconds. That's not a very small time, but let's assume it's 2.0 seconds. What's the impulse? The impulse is 200 newtons second. 100 times 2. But impulse is also change in momentum, isn't it? Therefore, using this idea, we can find the change in momentum. Let's assume that the mass of the object is 0.1 kilogram. Therefore, what is the change in velocity? Well, impulse is change in momentum. So delta P stands for change in momentum, which means it is mv final minus mv initial. I'm taking out the mass, and you can write it as m times vf minus vi, from which we can find the change in velocity, vf minus vi, just doing j by m. J, impulse, is 200 newton second, and the mass was 0.1 kilogram. So we get a change in velocity of 2000 meter per second. 2000 meter per second. So this is how we could use the concepts of impulse. So remember, there are two formulas for impulse. One is the product of force and time. The other is the change in momentum. And if we have a force-time graph, by finding the area of the graph, we can find the impulse. So here is a lab that we actually did. It's called the ballistic pendulum. The ballistic pendulum uses the conservation of energy and the conservation of momentum, both. And so I kind of like it. And you will find a question on the exam related to this. So what is a ballistic pendulum? It is a long string at the end of which you have something like a wooden block, and that is a ballistic pendulum. Ballast means heavy, so it's a heavy pendulum. Now imagine that you take a gun, hold it touching the wood, and fire a bullet into it. If the wood is really hard and big enough, let's assume that the bullet gets stuck in the wood. It doesn't come out the other side. If that happens, now the pendulum is going to swing up. So what do we have now? We have the wood and the bullet stuck inside, swinging up. So it's going to start moving up with a certain velocity, and it's going to reach a height and stop there and then come back. And from all of this, we can calculate the velocity with which the bullet was fired. In fact, before the age of computers, this was the mechanism or the method using which they would find the velocity of a bullet from a gun. We don't need it now, but we could still use it. So there are two velocities here, remember. In fact, there are three. The initial velocity of the ballistic pendulum is 0 because it's not moving. And then you have the initial velocity of the bullet with which it is fired. That's the second one. And the third one is after the bullet gets stuck in the wood, the velocity with which both of them start moving up. That's a third velocity. So let's apply the conservation of energy and momentum to find out the velocity of the bullet. So that is the diagram, and I'm assuming that the angle through which the pendulum moved up was 10 degrees. And that means the center of the object went up by h meters. See that? So the center was down here, it's gone up, that's h meters. First of all, we have to relate h to the angle. That's using trig, but we don't have to go into the details. It's going to be simply a relation that you have to remember. And then we have the mass of the bullet. We have the initial velocity of the bullet, which we're trying to find. We also have the mass of the pendulum, caps M. Let's assume that that is 1 kilogram. And that the mass of the bullet is 0.1 kilogram. We're trying to find that velocity. We do not know the velocity with which it's going. We do not know the height. But here is what I was telling you that you got to remember. Height is length multiplied by 1 minus cosine of the angle. So using that and assuming that the length of the pendulum is 1 meter, we can calculate the height. Let's do that. So that's 1.0 times 1 minus cosine of 10. Put it in your calculator, you get the height. Once you get the height, you have to remember that when these two together gain a height, they are actually gaining potential energy, which is mgh. The only thing is that in this case, m would be the total mass of both of them because the bullet is stuck in. But where did this potential energy come from? It came from the initial kinetic energy of both of them beginning their journey. So that's where we use the conservation of energy. mgh is equal to 1/2 times m plus m v squared. So on the left hand side, I actually had to put the total mass there. So I think I did a mistake there. So on the left hand side, I should have 1.1 kilogram. I will correct that and I will do the calculations again. And so that means the masses will cancel out on the left and the right side, and we will get a totally different velocity. But this is how you essentially do it. I'll put the corrected numbers very soon. But I'm going to show you what we need to do. Forget about the numbers. I will correct it later. What do you do after you get that initial velocity with which they start moving? You apply the conservation of momentum. And according to the conservation of momentum, mass of the bullet times velocity of the bullet, that's the initial momentum of the bullet. But the ballistic pendulum was not moving, that's why it doesn't have any initial momentum, should be equal to the total mass times the velocity which we get. So from this, knowing the corrected velocity and the masses, we can calculate the velocity of the bullet. That is the idea. Another concept that we need to know about is torque. So torque is something that produces the effect of rotation. And whenever we talk about torque, there must be two things. Number one, there must be a force. Number two, there must be a point at which the force is applied. So if this is an object, and let's say that it's hinged here, so it can rotate, or in other words, this is the axis, and if we apply a force, see, it rotates. Now how do you find the torque? Torque is simply how much force you apply multiplied by the distance of the force from the axis. So that distance. See that? But when you take the distance, it's got to be the perpendicular distance. So if you apply the force at an angle, then the perpendicular distance changes. It becomes smaller. So to get maximum effect, think about how you open a door. You would always apply the force perpendicular to the door and away from the hinges so that the door opens easily. So that's what I'm trying to show here. I've shown many forces. There is one force at B. There are two forces at C. And the axis of rotation is at A. So I was trying to tell you that to find the torque of this, first of all, this is a clockwise torque. Why? Because it's trying to rotate it clockwise. In fact, all three are trying to rotate it clockwise. How do you find the torque of this? The force, whatever it is, multiplied by distance AB. Okay? So torque is represented by the symbol tau, and it's RF sine theta. But if theta is 90, that's why I was saying applied perpendicular, sine 90 is 1. So then the formula just becomes R times F. That is torque. We're going to use this idea to find out an unknown force. Okay, we're going to do that. So torque is also given by I alpha. I is rotational inertia. Rotational inertia has different formulas for different objects. Okay, if it's a solid sphere, it is 2 by 5 mr squared. If it is a disk, it's mr squared by 2. So these are the two that you need to know. Again, a solid sphere, it's 2 by 5 mr squared. If it's a disk, it's 1/2 mr squared, same as mr squared by 2. So this is another relation. Torque is I alpha. What's alpha? Alpha is angular acceleration. So let's use this to find that before we use the torque concept, Let's go into rotational motion. You know, rotational motion, you have a lot of similarities with linear motion. You have the kinematics equations, which are going to be different now. And we're going to see how we can use that. So the question says, a flywheel is turning at 600 RPM, 600 rotations per minute. What is the angular speed? That is the question, that's all. A flywheel is turning at 600 rotations per minute. There is a flag there. We never measure time in minutes. It's got to be in seconds. So 600 rotations per minute. We have to change that into rotations per second. So then we get 600 RPM divided by 60, because there are 60 seconds in a minute, and that gives us 10 rotations per second. So that is called the frequency. RPS is called the frequency, little f is RPS. From there we can find the angular velocity. Got to know that angular velocity is 2 pi times the frequency. It's also theta over t, but in this case we just need 2 pi times frequency. Since we know the frequency is 10, just multiply by 10 and you get 2 pi times 10, which is 20 pi. Put in your calculator, you get 62.84 radians per second. That is the unit of angular velocity. So I'm continuing this question to say that if the radius of this flywheel, a flywheel is a disc, it's circular. If the radius is 20 centimeter, we could find the angular acceleration, alpha. And we could also find the linear speed. So let's find the linear speed. Now to find the linear speed, you got to know the relation between angular speed and linear speed, which is what's come up there. Omega is V by R. So substitute 62.84 is equal to linear speed by 0.20. Why 0.20? That's 20 centimeter in meter. And once you rearrange and calculate, you will get the linear speed. But the linear speed is in meter per second. So we get 1256.8 meter per second. Cut. So here is another question on rotational motion. Cut. On rotational motion. A wheel accelerates from rest to 40 radians per second at a uniform rate of 5.0 radian per second squared. It accelerates from rest. So its angular speed, initial, is 0. And its final angular speed is 40 radians per second and a uniform rate of 5.0 radian per second squared. So that's alpha. How do you know? Because you see the units, radian per second squared. Just like meter per second squared in linear kinematics. Through what angle did the wheel turn while accelerating? So it made a certain number of rotations. We got to find the total angle through which it moved while it was accelerating. So it started at rest and picked up speed, and then what's the total angle? So what is given? The initial angular speed is given, that's omega I, which is 0. Omega final is 40 radians per second. Alpha is given, and we're looking for angle. So you have the formulas with you. You have to pick the formula which contains theta, omega I, omega F, and alpha. And that would be this one. Omega F squared minus omega I squared is 2 alpha theta. Rearrange that to make theta the subject. You may need 1 or 2 steps. I've just written it in one step. That's what you get. Substitute the numbers given. Omega final is 40, so 40 squared minus 0 squared divided by 2 times 5.0, and simple calculation, and you do that. 40 squared is 1600 divided by 10, 160 radians. So that's the total angle through which the wheel turned while accelerating. There is a B part. In the B part, I think we're going to find the time, or how many rotations. We can find the time, we can find how many rotations or revolutions it made in making that angle. How do we do that? Well, because we know that in one rotation, the angle is 2 pi radians. 2 pi radians. So whatever we have, if we divide it by 2 pi, we're going to get the total number of rotations. That's what we do. And I've given it as a formula. Theta is 2 pi n, where caps n is the number of revolutions or rotations, which is what we're looking for here. So I've made that the subject, and we get 25.46 revs. Oh, this is where we're going to use torque. You know, if an object is balanced, like a meter stick is balanced, and in this case I think I'm going to have 2 points where it's supported instead of 1. So a meter stick is supported on 2 pillars, like a bridge is supported on many pillars. Let's assume there are only 2 pillars. And then we have to find whatever we are asked to find. We could find the mass of the meter stick, but in this case, we are given that the meter stick balances at the 51.0 centimeter mark. What does that mean? If an object balances at a certain point, that is the center of mass. So center of mass is the point at which you can balance an object. And what's so important about the center of mass? That is the point through which the weight of the object acts. So when the question says that the meter stick balances at the 51.0 centimeter mark, we know that whatever is the mass of this meter stick should be shown acting through that point. And then the question says if a mass of 25 grams is kept at the 80 centimeter mark, so 25 gram mass is hung at the 80 centimeter, then the stick balances at the 62.0 centimeter mark. What is the mass of the meter stick? This has always been confusing for students. So let's look at it again. If there is no mass anywhere on the meter stick, it balances at the 51 centimeter mark. Perfect balance. But if you have a mass of 25 grams kept at the 80 centimeter mark, somewhere here, then it balances at the 62 centimeter mark. See, if this is 51, you got to move the balance point. So now when you draw the diagram, you're going to show the 25 gram at the 80 centimeter. You're going to show the point of balance, which is the 62 centimeter. And do not forget, the mass of the meter stick is going to be shown at the 51 centimeter mark. Why? Because that is the center of mass. And then you have to find the mass of the meter stick. So this is, if you understand it, it's a simple thing. So that's the 25 gram mass at the 80 centimeter, and that's the mass of the meter stick at 51. All right, so it's balanced at 62. So now what we got to do is, you got to find the torque due to 25 gram. The torque due to 25 gram is 25 times 80 minus 62. Why? Because torque is force times the distance. Now in this case we are using gram, and that's okay because it's consistent. It's what we use on both sides. So anyways, 25 times the distance. So 25 times this distance. Isn't that clockwise? Yeah, it's trying to turn it clockwise. What is the mass of the meter stick trying to do? Trying to turn it counterclockwise. So that torque will be m times 62 minus 51, because that's the distance, see? M, and that's trying to turn it counterclockwise. Now all that remains is the math. 80 minus 62 is 18. 62 minus 51 is 11. So 25 times 18, you get 450. Divide by 11 and you get the mass of the meter stick as 40.9 gram. Now I hope you understood that in static equilibrium, you got to look at the clockwise torque, counterclockwise torque, and set them equal to each other. If there were two pillars, you would do exactly the same thing. Now this is where you have the two pillars. So let's do this. A 140 kilogram horizontal beam is supported at each end, so the two pillars. A 320 kilogram piano rests a quarter of the way from one end. So the length of the beam is not given. Instead, we are told that the piano is kept 1/4 of the way from one end. And what is the vertical force on each of the supports? The vertical force on each of the supports. Let's have the diagram come up. Oh, what is that? That is to be taken out. Okay. So, a diagram is always important in physics and more so in this case. So, here comes the diagram. And let me just clear this out. Much better. Okay, now. So that's the point. See, I've divided it into 4 parts, you can see, and that's the piano. I'm going to make that a little smaller. And that is the 140 kilogram. But now I'm changing it into newtons. You know, it's 140 times 9.8. What is that? That's the weight of the beam. And we know that the weight of the beam should act right through the center. That's why it's shown exactly at the center. That's the center of mass. And then what are these? These are the reactions at the two supports up. Let's call them F1 and F2. And then you have one more, which is the weight of the piano. It says 320 kilogram. So that's 320 times 9.8, which we get in newtons. That is 3136 Newton. And when you have two supports, you have to decide where you're going to calculate the torque. Okay? Probably I'm going to do it at the left end. Why? Because if I calculate the torque at the left end where F1 is acting, F1 does not contribute to the rotation because there's no distance between F1 and that point. So whenever you have two supports, you have to determine where you're going to calculate the torque because you got to measure all distances from that point. But before we do that, in static equilibrium, there are two conditions. The first condition is that the total up forces should be equal to the total down forces. How many forces do you have up here? 2. What are they? F1 and F2. Therefore, F1 plus F2 should be equal to these two acting down. So I'm going to add them. That's condition number 1. Total up is equal to total down forces. I add them, I got 4,508. Then the second condition is that the total clockwise torque must be equal to the total counterclockwise. For a third time, we got to determine where you're going to calculate the torque. So I'm writing calculating the torques about A. So I'm going to take all distances from there. Now what do these arrows show? These arrows show that this is trying to turn it clockwise, this This is also trying to turn it clockwise, while this is trying to turn it counterclockwise. What about F1? I told you it doesn't have any torque because it's right there. How do you calculate the torque? It's force times the perpendicular distance. So what would be the torque due to this? It would be 3136 times 1 by 4. So that's a quarter. What about the torque due to this? It would be 1372 times half, because that is half the length of the beam. What about the torque due to this? We don't know the force, so we'll put it as F2 times 1, because that's the whole length of the beam. And from there we can calculate F2. And you get F2 as 1470 newtons. And once you get F2, substitute that into this equation, and then you can get F1 is 4508 minus F2, which is 4508 minus 1470, and you get 3038 newtons. That's it. That's how you do it. Apply the two conditions for static equilibrium. Remember, when you're doing all these problems, I'm also giving you concepts that you got to listen to very carefully, because the multiple choice questions will be based on these concepts and others. Well, I was looking into the camera and recording without having hit the record button. It's happened so many times in my life. So that's why my face was missing for some time. And I did not have the time to re-record it. So let's move forward. Young's modulus. This is from, elasticity. So you got to know stress, strain, the definitions of these, and Young's modulus. Young's modulus is defined as stress divided by strain. And then you have this formula coming up. Y is Young's modulus, and F is the force up, and L is the original length. Delta L is the change in length. Because when you put that weight there, the cable is going to stretch just a little bit. And that is how you calculate Young's modulus. It's pretty straightforward formula. And here is a problem which shows how you can apply this formula. So here we have a steel cable, a steel wire, which has a load of 20 kilogram at one end. So that's the load. And it stretches by 1.5 millimeter, just a tiny bit. If the diameter of the steel wire is 1.0 millimeter, find the original length. So we have to find the original length, and we will be given the Young's modulus. So the Young's modulus of steel is 210 GPa. Now G there, caps G, stands for giga, which is 10 to the power 9. So it's actually 210 times 10 to the 9. So what's the force? The force is the weight of 20 kilogram, which is 20 times 9.8, 196 newtons. And area is pi r squared, which is pi times, what's given is the diameter. So you got to take half of that. That's why I have 0.5. See, 1 millimeter. So we have 0.5. Then I changed it into meters by dividing by 1000, which is the same as multiplying with 10 to the negative 3. So I have the radius in meters squared. And so you get this. So once you get that, and then you have the, what is that? I forgot to put the square. So anyway, so the change in length is 1.5 millimeter, which we have to change in a meter again. So that is 1.5 times 10 to the negative 3 meter. And Y is F by A times L by change in length. Substitute. Before that, we can make the length the subject. When we do that, you get the length is YA times delta L by F. And then substitute the values. I told you Young's modulus is 210 times 10 to the power 9. And then area is, we got that as 0.785 times 10 to the negative 6. That's the area. Change in length is 1.5 times 10 to the negative 3 meter divided by the force, which is 196 newtons. Okay? So when you calculate all that, you get the original length of the steel cable as 1.26 meter. That's it. Cut. So here is another question. This is from fluids. Now when we come into fluids, you have to understand that there are many ideas. You have to have the idea of density, relative density. So in this question, you are given the weight of an object in air. It says it's 10 newtons in air. And when you put it in water and find its weight, it's obviously going to be less because water pushes up. That's called the buoyant force. And therefore, it only weighs 8 newtons. So 10 newton in air, 8 newton in water, and the density of water is given as 1,000 kilogram per meter cube. You can see that there. You have to find the density of the object. Now, in order to do this, which is again another lab that we did, you should know that relative density of any object is the weight in air divided by the loss of weight in water. So weight in air divided by the loss of weight in water. Okay, so that's what is coming up here. And actually it doesn't suffer a loss of weight. It's something that appears to have happened. That's why it's called the apparent loss. And that loss is 2 newtons, isn't it? 10 minus 8, it appears to have lost 2 newtons. That is the buoyant force. Should also know that that's called the buoyant force. Because maybe on the exam, I'm going to ask you the buoyant force. Okay? So we could do this in 2 ways. And this is the second method that I'm showing here, more important. You have to know that the buoyant force is the volume of fluid displaced times the density of fluid times G. Very important formula. We know the buoyant force is 2, so we put 2 is equal to, we do not know the volume of the fluid displaced, which we can get now. Because we know the density of the fluid is 1,000 times G is 9.8, so we get the volume of fluid displaced as 2.04 times 10 to the negative 3 meter cube. Now hold on. Since the object is completely immersed in the fluid, the volume that is displaced must be the volume of the object. So we got the volume of the object. And we also know its mass. Do we know its mass? We know its weight. If you divide that by 9.8, you will get the mass. And then knowing the mass and the volume, you can find the density. So that's the idea that I've used here. So the volume of fluid is equal to the volume of the solid, which is given. We know the mass is 10 divided by 9.8, which is 1.02 kilogram. Density is mass divided by volume, isn't it? So divide the mass by the volume and you would get a number, which is the density of the solid. Now, what we're getting 1,002 kilogram per meter cube, because the volume of the fluid was 2.04 times 10 to the negative 4. So we get 5002 kilogram per meter cube. Relative density is what? Weight in air divided by loss of weight in water. What was the loss of weight in water? Wasn't it 2 newtons? So what is the relative density? 10 divided by 2. 10 divided by 2. Its relative density is going to be 5. Correct? If the relative density is 5, then the density of the object is just that times 1,000. Whenever you get the relative density multiplied by 1,000. So it is 10 divided by 2, 5 times 1,000 is 5,000. Angular momentum is another topic that you need to know. Angular momentum. It's the product of I and omega, where I is rotational inertia, and I can be mr squared by 2 for a disk. And if it's a solid sphere, I did mention before that it is 2 by 5th mr squared, okay? But if it's a disk, and assuming that the mass of the disk is 2 kilograms, and which you can see there, and its radius is 0.2 meter, we can calculate the rotational inertia, and you get it as 0.04. Notice the unit of rotational inertia is kilogram meter squared. And then let's assume that it's spinning at the rate of 3.0 radians per second. All you got to do is multiply the rotational inertia with the omega, and we would get the angular momentum. So angular momentum is the rotational counterpart of linear momentum, okay? So that is angular momentum. And also remember that angular momentum is conserved. You've done a lot of assignment questions on this, and so you should be aware of conservation of angular momentum. So that's about angular momentum that I've written there. So the question is, what is the kinetic energy of this disk? So on this left-hand side, I'm showing you conservation of angular momentum, which is I1 omega 1 is equal to I2 omega 2, but it comes with a condition that there is no torque acting on the system. So angular momentum is conserved only if there is no external torque acting on the system. So going back to how do you find the kinetic energy? The formula for kinetic energy of rotation is 1/2 I omega squared. So 1/2 I omega squared. I, we got 0.04, omega we got here, square it, don't forget, and you will get the rotational kinetic energy as 0.18 joule. So we're coming to the end of this review. There are a couple more things that I want to tell you, and this is one of them. What is the pressure at a depth of 20 meters in fresh water? Here, I'm trying to remind you that when you calculate the pressure due to a liquid, you use the formula H rho G. H is the height of water, rho is the density, and G is acceleration due to gravity. In this case, the height is given as 20 meters. We know the density of water, fresh water, is 1,000 kilogram per meter cube. And G is, of course, 9.8 meter per second squared. So knowing all that, you can calculate the pressure due to water. And that comes out to be 196,000 pascals. The unit of pressure is Pascal. This is called the gauge pressure. If you want to calculate the total pressure, you have to add the atmospheric pressure to the gauge pressure. So you got to add the atmospheric pressure to the gauge pressure, okay? So the second part of the question says, what force? Let's see what that says. What force acting on a circular plate of 20 centimeter diameter at the depth? Okay, what is the force? or what force acts on a circular plate of 20 centimeter diameter at the depth. So you're given an area of a circular plate kept at that point, and you got to find the total force on that. I'm just trying to show you that pressure is basically force divided by area. So since we got the pressure at that point, you can manipulate this to find the force, which is simply pressure times area. And that gives you P times pi r squared because it's circular. And then the pressure is 19,600. When you do that, you get 6,157.5 newtons. So that is how you do pressure and force calculations due to a liquid. The last topic here is Bernoulli's Principle. And there will be just one problem on this, but it's important. Now, the diagram or the picture shows a car and an 18-wheeler just passing by on two adjacent lanes. What happens is the air between the two is going to be moving very fast because the air is being pulled in both ways, so it will move very fast as compared to the air around them. So in these regions, the air is not moving that fast, but here air is really moving fast. And according to Bernoulli's principle, where the speed is higher, where it is faster, the pressure is lower. Can you remember that? Where something is moving faster, like a liquid or a gas is flowing faster in a region, there the pressure becomes lower. That's another reason why hurricanes are very dangerous. Because when the wind blows over the roof of the house at a great speed, the pressure becomes low. So inside the home, the air is virtually not moving. But on top of the roof, the air is moving so fast. And where it's moving fast, the pressure is low. So what happens? The entire roof faces a force acting upwards because there's low pressure on top, high pressure below. It's like pushing it up. The roof gets blown away on many occasions. This is exactly why cars are lifted up and thrown when there is a fast wind blowing. So that is the impact of Bernoulli's principle, and we'll work out a problem soon. But I wanted you to see the formula. The formula that we get for Bernoulli's equation is from a tube which is wide here, narrow at the other end, and it's also kind of inclined. And so imagine that there's a liquid flowing up. The flow velocity here is V1, here it is V2. The height here is H1, here it is H2. So the potential energy here is mgh1, and the kinetic energy is 1/2 times mass times velocity squared. We know potential and kinetic energies. But for a flowing liquid, there is a third type of energy. It's called the pressure energy, and that's simply the product of pressure and volume. So the total energy, potential plus kinetic plus pressure energy, is a constant. That is Bernoulli's principle. Make note of that. And then I divide it throughout by volume. And when I do that, mass by volume is density. Again, here mass by volume is density. And here the volumes simply cancel out. So that's why we get the equation for Bernoulli's principle this way. Whenever I ask you problems, it will always be for a horizontal pipe. So it won't be inclined, which means the potential energies are equal. So we can remove that potential energy term, which is this one. Where is the potential? Yeah. So that term can be removed. And therefore, for a horizontal pipe, we can simply write, my goodness, that's, okay. So when we remove this out, what we have is going to be P plus 1/2 rho V squared is a constant. So that is how you should remember it. And you will soon see how we can work out problems using that, okay? Now remember, this wind is blowing at 35 meter per second over a house. What is the net force on the roof if its area is 240 meters squared and it's flat? So just imagine it's flat. It doesn't make a big difference if it's not flat. So you're just given two quantities. You're given the air speed over the roof, but below the roof we know that the air speed is virtually zero. So how do we find the force? Find the force by pressure times area. In this case, it would be the pressure difference times area. So we're going to call the top and the bottom 1 and 2. So you have P2 minus P1. So P2 is the pressure. It's a flat roof. Why did I draw it like that? I'll change it when I see it. Okay, so pressure is P2 below the roof and P1 above. And this is Bernoulli's principle. P1 plus 1/2 rho V1 squared is P2 plus 1/2 rho V2 squared. So flatten it. Okay. And we're looking for P2 minus P1. In fact, yep. So that would give you 1/2 rho V1 squared minus V2 squared. I just took out 1/2 rho, and then the force would be that quantity multiplied by A. You see that? So instead of this, I'm going to substitute this whole thing and multiply it with A. And then you need to know the density of air. Not need to know, it'll be given. It's 1.29 kilogram per meter squared. Kilogram per meter cubed, sorry. And so substitute the velocities and marking the velocities there. V1 is 35 meter per second, V2 is 0. And see, again, I mixed up P1 and P2 there. Okay. That's P1, that's P2. And it doesn't change anything mathematically, but you have to know P2 is greater than P1. That's why we took P2 minus P1. And V2 is 0, so there's nothing there. V1 is 35 and area is 240, and you get this. Look at that force. It's such a huge force that you get acting on it. It's 1.9 times 10 to the 5 newtons. Okay, such a big force. So those are the main topics for exam 3. Doesn't mean that you do not study anything else, but focus on these. There are also other review videos that I've made from the other semesters. Please also take a look at those. Thank you and wish you the best.